Hello everyone, this is Michelle here. Today we're going to talk about minor losses. If you remember in last chapter, we introduced you the Darcy's equation, and it's written like this, where F is a friction factor that you can find it in the Moody diagram. We use this equation to evaluate the head loss associated with frictional effect in street pipes, which we call it the major loss. But most pipe systems does not only have straight pipes. For example, a system like this, and you can find this picture in our um, textbook. And in a system like this, we'll see some valves or T's or elbows and the bands. Um, so when flow passes through these bands or valves and the fittings, um, it will have some additional head loss due to flow separation. Or when flow passes through, um, for example, from a large pipe into a small pipe, they will experience some sudden geometry change, and which means the flow has to accelerate in a particular local area to pass through, and that will cause additional head loss as well. So therefore, the overall head loss, HL, has two parts. It's the major loss, we call it HL major, and the minor loss, we call it HL minor. Please note this word major and minor um, does not really reflect which one is more important or not. Um, Sometimes when pipe is very short and has a lot of components, the minor losses may be even larger than the major loss. There are two ways to calculate minor losses. And the first one for minor loss in bands, sorry. For minor losses in bands and valves and fittings, the equation is very similar as the Darcy's equation. So let me write it down for you, and I'm going to explain that later. So the HL minor, for the case like in the bands and valves and fittings, we write as Ft times Le over D, and then V squared over 2G. So it's very similar as Darcy's equation, and the only difference is Ft number and this Le number here. So what is Ft? Ft is the friction factor at the complete turbulent zone. Okay, let's have a look at how we get the Ft number from the Moody diagram. On the Moody diagram, we have this dashed line here, and we said the area above this dashed line is called the complete turbulent zone. And in this zone, the curves of this friction factors turns into almost horizontal lines there, which means they are independent from Reynolds number. So to read the Ft number, we basically just need to find out the relative roughness number, which is from the material of the pipe, and then find the curve. For example, if I'm using this relative roughness is equals to 1,000. So I'm going to get this curve, and then I find the cross point right on the dash line on the curve, and then read the friction factor on the left side of the Moody diagram. So you do not need to calculate Reynolds number to get FT. Textbook also gives a table on page 242, and this table is for us to get FT number for Schedule 40 steel pipe. And be careful, this table is only for new clean pipes, and if you have a used pipe, it doesn't apply. Okay, back to this equation. So we have another number we want to discuss, which is the LE number. So what is LE? LE is called equivalent length. And this equivalent length is the one of a same diameter straight pipe that cause the same resistance as the component we use. So normally we do not get a real LE number, we get a LE over D ratio here. And of course this one is dimensionless. Okay, here's a table for us to get the equivalent length ratio, LE over D, for different components, and it's on page 242 in our textbook. And you can tell this is for the different components. This is for the valves and elbows, bands, and tees. If you're not very familiar with those components, the book gives some introduction on those pages. You may want to do some home reading. This table actually is missing the equivalent length ratio for pipe bands. Some students may ask what's the difference between the elbows and bands. Well, the elbows are standard separate parts, and the bands are when large radius allows, sometimes it's easier to just bend the pipe than use a separate standard parts like elbows. So here's the chart for the pipe bands. And notice this chart is only for 90 degree pipe bands only. It's actually a very interesting chart if you notice the curves, the minimum number occurred at this area from 2 to 4, so that's kind of the best relative radius ratio for a 90-degree pipe bands to get the minimum resistance. So it's some area over here. When calculate the minor losses due to sudden geometry change, the equation is actually very easy. We just need to use the resistance coefficient K number and times V squared over 2G. So that's the thing we need to figure out. And pay attention to this velocity here. This V has to be whatever the higher velocity in the system. So for example, if you have the flow going through a small pipe to a larger pipe, based on the continuity equation, the velocity at the smaller pipe should be much larger than in the large pipe, so we're using this V1 number here. And in another situation, if the flow is moving from the larger pipe to a smaller pipe, here the V2 here is a higher velocity, so you have to use V2 in the second situation here. The resistance coefficient K number is related to the higher velocity, which the V1 over here, and also the diameter ratio. Okay, the book gives a whole bunch of different charts and like this, and different tables like this for different situations there. I'm going to put a detailed handout in our Moodle site, so have a look at that document later. I want to mention one more thing here for the entrance loss, and that's on this page here. So if you are using an old version textbook, you may find out the K number listed in your textbook is different from this one, so correct it based on this most recent number here. Okay, so that's for the minor losses. If you have any questions, let me know, and I'll see you next time.